Hello. In this lecture, we are going to discuss about the same topic, chemical reaction and equations. We are continuing the same chapter right now. So before moving ahead, let's talk about how we represent a chemical reaction or how we represent a chemical equation. So the very first method is a very simple one, that is word equation. Second is a skeletal equation, and third is a balanced chemical equation. So, if we are going to write an example, magnesium reacting with oxygen gas, forming magnesium oxide. So, this chemical reaction is a very famous reaction for burning of magnesium ribbon. That's a white color ribbon with a dazzling white flame. So, we get magnesium oxide, white color powder. So, this reaction takes place in the presence of oxygen. So, this is how we are going to write the word equation. Now, if we have to write in the equation, the symbolic equation, skeletal is the symbolic version of the chemical equation, the word equation we are going to write in the symbols, but this skeletal equation is very much unbalanced. So the same reaction, magnesium, we are going to write the state of matter also, reacting with oxygen gas. Oxygen gas is always going to be diatomic. In the equation form, we are never going to write oxygen as single O. That is what we call as nascent oxygen. So this is in the gaseous form. And we will get magnesium oxide, MgO. That's also in the solid form. So this is what we call a skeletal equation that's unbalanced. So if we need to balance this chemical equation, so magnesium is already balanced. So if we need to balance oxygen, if we put 2 as a coefficient in front of magnesium oxide, that indicates magnesium is 2 atoms and oxygen is 2 atoms. So it's balanced with respect to oxygen, but we need to put additional magnesium over here. 2 atoms, or you can say the coefficient in front of magnesium. Now this is a perfectly balanced equation. Now, this is very much okay when we are talking about the practical terms. But if on the theoretical grounds, if we say the stoichiometric coefficient, we don't want this magnesium to be 2 atoms. We just want 1 or 2 moles. We just want it as 1 mole. So if we cannot increase this coefficient, this is a perfectly whole number balanced equation that we have written over here. But what in the same equation, if we don't want to take 2 moles of magnesium over here or 2 atoms of magnesium, we don't want to do that. But we have 2 oxygen atom on the left hand side, and on the right hand side we have only 1 magnesium atom. So how to balance these? So on the theoretical grounds, we can just put half. This 2, this number, and this number will cancel off. So left over will be 1 oxygen atom. So this will be something like half into 2 atoms. So this will cancel and we will get 1 oxygen atom on the left hand side. and even on the right hand side. Now, this is a fractional stoichiometric coefficient. We don't use fractional coefficients for these kind of compounds where two different elements are there. So just remember, fractional coefficients can be used only for the molecules of the same element, like oxygen gas, hydrogen gas, nitrogen gas. So we are never going to use any kind of fraction for these kind of compounds because we have different elements that will just make the whole equation complicated. So we don't want that. But this is a possibility. So if there is a question, if 1 mole of magnesium burns in air to form 1 mole of magnesium oxide, then how many moles of oxygen gas are required? So when we say 1 mole over here, they are talking about the equation, the perfectly balanced equation that we need to have. So again, we are going to write this. So 1 mole, that means I cannot increase the coefficient. So this is R1, and magnesium oxide formed is also 1. So how many moles of oxygen gas are required? So it will be half. So answer will be half, or we can just write it as zero point 0.5 mole. So this is how we can solve these kind of questions. This is a direct question. I didn't put it in the MCQs, but this can be converted into multiple choice questions also. Moving ahead, next that we are going to discuss is, we already discussed characteristics of chemical reactions. We are going to do it again from the equations point of view. So the very first reaction that we can talk about is evolution of a gas. So we are going to add few more characteristics apart from what we discussed before. So evolution of any kind of gas is a very important characteristic which is going to govern that the chemical reaction is definitely taking place. So the chemical reaction that I'm going to take over here is a special reaction of potassium chlorate decomposition. So we are going to heat it. So just remember, in the future reactions, instead of heat, I'm going to use this symbol, something called as delta. It's okay to use this symbol in certain chemical reactions, and we can write heat, both are okay. So it indicates that heat is provided in the specific reaction. So potassium chlorate is a solid white color powdered form. It's a salt. So if we are going to take it in the test tube, and if we are going to heat it, then what products we are going to form? So it's going to give potassium chloride, which is another kind of salt, and oxygen gas is going to be released. Now there's a special reaction. This is also a very famous laboratory method for production of oxygen. So now we can produce oxygen in the lab with this salt. So now we have written evolution of a gas. Now, there can be multiple aspects of this chemical reaction. First, we can also call it as a decomposition reaction. So, about this, we'll be discussing in few minutes. So, decomposition is when you have only single reactant and you're giving multiple products on the right hand side. So, from a single reactant, multiple products, it can be one product, it can be more than one. So, that's a decomposition reaction. Decomposition means we are decomposing something, we are breaking up something, and it has to be a single reactant. So, decomposition can take place in the presence of heat, it can take place in the presence of electricity, in the presence of sunlight. So, there are three types of decomposition reactions that we're going to discuss further. So, this reaction can be used as an example for evolution of a gas, for decomposition reaction, and to be more precise, this can be thermal decomposition reaction because we have written heat over here, so there is temperature involved. One more thing, this potassium chloride and oxygen gas is getting formed. So we can write this equation always in the word form, that if we have metal chlorate, so if we are heating, we will get metal chloride and oxygen gas. I always try to remember equations in this format. So if you know the reactant, what is the raw material, what is the starting material, and you know what is going to be formed on the product side, then it's easy to write the equations. Now, for writing equations, we need to have a strong command on the chemical formulas, because if chemical formulas are not good in our head, we won't be able to write chemical equations properly. And there is a single subscript mistake. If we say instead of 3, you have put 4. So KClO4 is potassium chlorate, it's not chlorite. This we had discussed in the basics part lectures, previous lectures. So if it is KClO4 and if you have done that mistake, so obviously it will end up the whole balancing part. It will be very difficult or it will be wrong. So we need to be very careful when it comes to chemical formulas, what subscripts you're using, the fair formula is correct or wrong, because that plays an important role in the balancing of chemical reaction. So coming to the balancing part, now if we want to do on the whole number front, that means we want the stoichiometric coefficient to be whole number, right? We don't want to be a fraction, for instance. So if it's going to be a whole number, so we can see that we require KCl is perfectly balanced potassium and chlorine atoms. So oxygen we have 3 atoms on the left hand side, right hand side we have 2 atoms. So if we just crisscross, we put the opposite numbers. So if I put 3 over here and if I put 2 over here and 2 in front of potassium chloride. So this is perfectly balanced equation. So this 2 indicates there are 2 potassium atom, 2 chlorine atoms. There are 3 into 2, 6 oxygen atoms, and on the right hand side we have 6 oxygen atom and 2 KCl. So it's perfectly balanced. Now, what if we are going to do the same thing what we did before? If we want fractions, so KCl is in the solid form and oxygen gas. Okay, so now we don't want this to be increased. So we can make a question. If 1 mole of potassium chloride, sorry, my mistake. I said KClO4 is potassium perchlorate. Just remember that. See, it can happen with me also, it can happen with anyone. KClO4 is potassium perchlorate, whereas this is perfectly fine, potassium chlorate. So I wrote metal chlorate, potassium chlorate. So KClO4 is potassium perchlorate. So we can write the other examples KClO, KClO2. So this is potassium hypochlorite, and this is potassium chlorite. So about these examples, the chlorine oxoanions I've discussed in the previous lectures also. So now let's come back to this equation. If we are going to take this as 1 mole, then they are asking how many moles of oxygen are going to be formed. So 1 mole of KClO3 will definitely give us 1 mole of KCl. So how many moles of oxygen we are going to get? So it's going to be 3 by 2. Again 3 by 2 into 2 oxygen atom. This will cancel and we will get 3 atoms of oxygen like this. So this 2 and this 2 will get cancelled. So we have on both sides 3 oxygen atom. So if they are going to ask, then how many moles of oxygen are going to be formed? So it's going to be oxygen moles. Answer is 3 by 2. So it's only for 1 mole. If we don't increase the mole, for 2 mole we know the answer is 3. So for 1 mole it's going to be 3 by 2. So we need to understand these kind of questions. Then one more added aspect to this equation is the use of positive catalyst. So the positive catalyst that we can use over here is manganese dioxide. That is somewhere brown to black color solid. It's a solid. So it's going to increase the rate of reaction because we require high temperature for this particular reaction. So it can be used as a catalyst just to lower the temperature required. Now we don't have to memorize the temperature for every particular reaction. It's very much tedious to remember and it's difficult to remember, I would say. So not for every reaction we need to remember, but yes, we should remember the special aspect, at least the catalyst. So since we are heating, so it has to be a positive catalyst because heating requires to increase the rate of reaction. That means without this catalyst, a lot of high temperature is required for converting potassium chlorate into potassium chloride and oxygen gas. So in the presence of this catalyst, we can actually achieve the same process at a lower temperature. So the second characteristic that we are going to discuss is change of color. So in change of color, we can take this reaction Pb3O4. So again we are going to heat it and we are going to get PbO plus oxygen gas. Now this reaction can be used for multiple types of reaction. So the above reaction I wrote this, it's a thermal decomposition reaction. It can be an evolution of a gas. Plus we can even call this as a redox reaction. About redox reaction we will be discussing very later on, not in this lecture. So change of color. Now this is very much red in color. This is a red powdered form. We call it as red lead oxide, or we can even call it as tri-lead tetroxide. So this is solid in form. So again we are going to heat it and we are getting lead monoxide, which is yellow in color. Now if you think how to remember all this, yes, we have to remember because it's experimental. So if you're having any of these things in your exam, something related to in your syllabus, definitely we have to remember. Now depending upon different boards and internationally, there are different parameters. Sometimes they provide some information during the examination before the test, sometimes they don't. So if you can have these things in your mind, if you can practice and learn in a better way, so chemistry can become easy. So this oxygen is in the gaseous form. So now in order to balance this, we can balance again in the fraction way, we can balance in the whole number coefficient way also. So we can see that there are three atoms of lead on the left hand side over here. So if we are going to put 3 in front of lead, our lead is balanced on both sides. So oxygen, if you see, there are 3 oxygen over here plus 2 oxygen over here. So it will be 5 oxygen atoms. We have 4 over here. So what we can do? Can we make this oxygen as half? Now this half and this 2 will get cancelled, so we will have 1 oxygen atom. So if we add it up, 3 oxygen atom over here, 1 over here, so 4 oxygen. It's a perfectly balanced equation, but we are taking help of the fractional stoichiometric coefficient. Now if we need to write it as a whole number, now there is another way. So if we don't want the fraction, so write the same equation, Pb3O4. So we will get PbO, and we are going to get oxygen gas. So we use this 2 number over here, this 2. So multiply this entire equation into 2 if we do. So this will become 2 Pb3O4. Then this will become 2 into 3, that is 6 PbO. And this 2 if we are going to do, so it's already half over here, half into 2 into 2. Like, let's say this will become, already half is there, so half into 2, if we multiply, this will again become 1. So we'll keep it like this. We are not going to change any coefficient for this. So now we have 2 into 3, 6 atoms of lead. We have 6. 4 into 2, 8 atoms of oxygen on the left hand side. 6 oxygen are over here. 2 oxygen atoms are over here. 6 plus 2 is 8. So we balanced it. Now coming to the category of the equation, like how we can categorize this equation. So this can be called as a thermal decomposition reaction, because again we are decomposing. So whenever we need to find a thermal decomposition reaction, we need to see the left hand side. We need to see the left hand side, the reactant should be just one. There shouldn't be two reactants, there should be only one reactant. That's the identity of decomposition reaction. So we can call it as thermal decomposition reaction. Then most of the chemical reactions are redox. So this is definitely redox reaction, except for certain neutralization reactions, but most of them are redox. Then we can change in color. That's the characteristic we are talking about. So we can characterize these two, like we can name this equation like this: redox thermal decomposition. So change of color is done. Now we go to the third one. The third one, we are going to discuss about formation of precipitate. Now precipitates, I've already told what are precipitates. They are insoluble substances which are formed during the chemical reaction. It settled down at the bottom. And precipitates can be of multiple colors. So they are insoluble chemical substances. So whenever we have two chemical reactants mixed together, so after the chemical reaction, one of them is going to solubilize and the other is going to remain insoluble. And the state of matter for a precipitate is solid state. So let's take an example. We have silver nitrate, AgNO3. So we are going to use the term aqueous. Aqueous meaning anything dissolved in water. Aqueous, anything or any chemical substance? Dissolved in water. So just remember the solvent that we are going to take over here is going to be water. No, the solvent we are taking as of now. So silver nitrate AgNO3 is a white color salt. And if you make it react with NaCl, again aqueous, that is our sodium chloride. So we are going to get AgCl, that is the precipitate in the solid form, and NaNO3, which is in the aqueous form. So, how to make this equation? It's a type of precipitation reaction. It's a type of double displacement reaction. All these we'll be discussing in the next lecture. So, how to make this reaction? So, Ag is a cation. It's cation. How do I know? Because in the chemical formula, Ag is somewhere written on the left hand side of the chemical formula, whereas nitrate is a radical. It's an anion, it's a negatively charged. How do I know? Because it's written on the right hand side of the chemical formula. So this cation is going to be attracted towards anion of the other chemical reactant like this. And we are going to get AgCl, and we are going to get NaNO3, that is sodium nitrate. So silver chloride, and this is our sodium nitrate. So if we split it, Ag plus NO3 minus Na plus Cl minus. So we can make the products. Ag plus definitely will be attracted towards chlorine, and Na plus will be attracted towards nitrate because opposite charges will attract. So the whole chemistry is based on this only. Opposite charges attract, unlike charges repel. So this AgCl silver salt, silver chloride formed over here is white precipitate. The color of this insoluble substance in the test tube that we will get is white in color, and that we have to remember. There are not many precipitates that we need to memorize, but yes, as of now, if we can remember, AgCl is a white color salt, so that will be beneficial. And sodium nitrate, since I've written as the aqueous form over here, so it's very much soluble in water. So what we are doing in this equation, we have taken white salt AgNO3, we took some, you can say, some grams of AgNO3, any grams or maybe a pinch or maybe a little bit, depending. We don't have a set amount that we can use. We can use any little amount in the test tube, put some water in it, make it aqueous solution, then in a second test tube take NaCl, add some water. So we have two aqueous solutions, separate test tubes. Now in the third test tube, mix both the contents of these two test tubes. Immediately you will get AgCl white color salt at the bottom, and you will get aqueous solution that will be definitely of NaNO3 sodium nitrate. Now moving to the next equation. So let's take two examples over here. So we have PbNO3 whole twice. This is aqueous again. We call it as lead nitrate. So it is going to react with potassium iodide. And one more thing, this is a perfectly balanced chemical equation. We don't need to put any stoichiometric coefficient in front of it. So potassium iodide, which is aqueous, PbI2, and we are going to get potassium nitrate. So this is PbI2 is going to be solid state because it's our precipitate, KNO3 is our aqueous. So this is potassium iodide, and this is lead iodide, and this is potassium nitrate. So again, we can do this PbI2. Now why PbI2? We don't have to apply maths over here. Lead, I can see from this particular number that the charge of lead is Pb with the +2 charge. And there is no number over here, that means nitrate we did over here also, it is NO3 minus. So potassium, no number, so it's K plus. And then I minus. So again, these will be attracted towards each other. So when you crisscross the valencies for lead, lead is 2, I is 1. So when you crisscross, you will get PbI2 as a chemical formula, which is a lead iodide. Now the color of this precipitate is very much yellow. So we can remember AgCl is white color precipitate. Most of the silver salts uh, are insoluble. They are always going to form precipitates. Most of the silver salts, they can form different colors that we can talk later on, but they are always going to form insoluble salts, precipitates. So lead iodide, which is yellow color precipitate, you have to remember